Dear students, today I am posting my next video on Schmitt Trigger, the application of Opamp operation amplifier, where Opamp is being used as a Schmitt Trigger circuit. Now, what is this Schmitt Trigger and how does it work? We will see. So the heading will be Schmitt Trigger. Now, if you go to see the basic definition of Schmitt Trigger, it is a regenerative comparator circuit. That means it is going to compare two inputs. One of them will be a sine wave input, and the other one will be a reference voltage, which will be derived from the output of the same circuit. Okay, so if you see the definition here, Schmitt trigger can be defined as it is a regenerative comparator. It employs positive feedback and converts sinusoidal input into a square wave output. Okay, that is obvious, that we'll see as we see the circuit. The output of Schmitt trigger swings at upper and lower threshold voltages, which are the reference voltages of the input waveform. It is a bistable circuit in which the output swings between two steady state voltage levels, high and low, when the input reaches certain designed threshold voltages. Now, all these levels, when the output have to be changed, when the output will go to plus V saturation or minus V saturation. Okay, all that depends on the feedback what you give from output to input as a reference voltage, the positive feedback what we give. Now, if you see another a definition, a Schmitt trigger is a comparator circuit with hysteresis. So there will be a hysteresis form that we'll be speaking lastly, which will be implemented by applying positive feedback to the non-inverting input of a comparator or a differential amplifier. It is an active circuit which converts an analog input into a digital output signal. This is where we see that sine wave is converted into square wave. The circuit is named as a trigger because the output retains its value until the input changes sufficiently and it reaches some threshold voltage, and then only the output will change. There will be a trigger change. Okay, so that is why it is called as a trigger circuit. Now, if you see a simple Schmitt trigger circuit over here, so here you have shown a op-amp, and op-amp is been given with a inverting input here, and you have a non-inverting feedback. So there is a positive feedback. So here you can see there is a positive feedback here. So here you have shown a positive feedback. This is a positive feedback. This is important, which is going to come from this point of voltage dividing network. And here you are having a resistor R1 and R2. So voltage across this will be coming as a feedback. So this voltage you can call it as V1 if you want, and this will be coming as a feedback voltage. Now the input is given to the inverting terminal. The input is given here. This is the input. It has been given to the inverting terminal. Okay, so this is your inverting terminal. Now this input is say a sinusoidal wave. This input is sinusoidal wave. And this output or this feedback, whatever you are going to give, will be a stable voltage for some time. That is called as V1, which depends on the values of R1 and R2. And that will decide when the output has to change its state. Now, if you see a superposition or superimposing of the two inputs, if one input was a sine wave like this, okay, now this is a regenerative or comparator circuit. So one comparison, one threshold voltage will come here, which will be called as upper threshold voltage, and one voltage will come here, which will be called as lower threshold voltage. Now the points where you see this, when the input goes above the upper threshold voltage, when the input goes below the threshold voltage, when the input goes below the lower threshold voltage, and when the input goes upper the threshold voltage, upper the lower threshold voltage. So this is your reference voltage, and this is also is a reference voltage. So both sides you're going to have reference voltage. So depending on how the input is moving, and depending upon input is more than which threshold, the feedback will produce the particular threshold voltage. The feedback will produce the particular reference voltage. And depend upon that reference voltage, the output will change its state with the maximum voltage that op-amp can give, that is plus Vsat to minus Vsat, that is plus V saturation to minus V saturation. Okay. That means now here you are going to have a comparator whose one input will be a sine wave, and the other feedback, whatever you are going to give to the positive terminal, that is non-inverting terminal, will be, there will be two types of reference voltages. One will be your upper threshold voltage UTP, and second one will be your lower threshold voltage LTP. Now those will be generated again by using the output only, and because it is generated on its own depending upon the output only, it is called as regenerative comparator. Okay. So depending upon the comparison of both the inputs, the output is going to change its state in only two levels. Either it will be plus V saturation or it will be minus V saturation. So it is like a square wave at the output. So we can say that if you are giving the main V in input to the inverting terminal here, that is a sine wave, then output will be a square wave. So here you can see the output can be a square wave where it is going to change its value from plus Vsat to minus Vsat. So you will get output of this kind. You will get output of this kind depending upon the comparison of the two things, that is the sine wave and the reference voltage. So here this can be your plus V saturation and this can be your minus V saturation. So in general, we can say that sine wave is converted to square wave or analog wave is converted to digital wave. Okay. So this is how a comparator circuit, a comparator circuit with positive feedback and inverting input, it is going to work as a Schmitt trigger. So practically again you can see the same type of circuit. We have V in and then R1 and R2 are given a value, and then you have plus VCC and minus VCC supply, and you will get output. So same circuit has been shown practically over here. Now, if you go to give the explanation of Schmitt trigger, then we can give it as a part of output is fed back. Okay, a part of output is fed back to the non-inverting positive input of the op-amp. Hence, it is called as positive feedback comparator. Okay. Now, there is some calculation by which you can calculate the upper threshold voltage and the lower threshold voltage. Okay, so the triggering point Vt should be calculated first, and that Vt will be calculated as Vt is equal to, okay, R2 resistance upon R1 plus R2 multiplied by whatever V out you get. Okay, if you do this, you will get the triggering point Vt. Okay, now if Vt is positive, then output is equal to plus Vsat. If Vt is negative, then output is equal to minus Vsat. Okay. Thus, when output is plus Vsat, the upper threshold point is given as, now this is important, the upper threshold point Vut is given as R2 upon R1 plus R2 into plus Vsat. This is your upper threshold voltage, upper threshold point. Okay. Similarly, you can have a lower threshold point when the output is minus Vsat, and that can be given as VLT is equal to R2 upon VLT is equal to R2 upon R1 plus R2 into minus Vsat. This will be your LTP point. Okay, lower threshold point. The operation of the above circuit can be explained with the two conditions. That is, when V in is greater than Vt, V out is equal to minus V saturation. And when V in is less than the threshold, V out is equal to plus V saturation. This you can see in the waveforms also. Okay. The operation of the above circuit can be explained with two conditions, as I've told you. When V in is greater than Vt, V naught is equal to minus Vsat, and when V in is less than Vt, V naught is equal to plus Vsat. So this is how it is going to vary at the output. So when input voltage V in is less than UTP, that is upper threshold, the output is positive saturation. When the input crosses the upper threshold, okay, the output will change to negative saturation. This output state is maintained till the next threshold level, okay, that is VLT, that is lower threshold voltage. When input signal crosses the lower threshold VLT, output is changed to positive saturation. So this you can understand only if you see the waveforms. Okay. Now the last definition over here. Thus, output state is changed only when two thresholds are crossed. This is shown in the transfer characteristics. Between the lower threshold and upper threshold, output plus minus Vsat remains constant, and that is output is not responding to any changes in the input signal. Thus, output is dead between VLT and VUT, and this condition of dead band is called as hysteresis. This also we can see when we observe the waveform. So here you can see this is the waveform, a simple waveform shown. Now the sine wave which you are going to show, which you apply to the inverting terminal, is this sine wave. This is a sine wave, or you can call it as analog wave. Okay, so this will be your sine wave, or it can be called as your analog wave because it is continuously varying with time. Okay, and depending upon your R1 and R2 resistances, you have calculated this reference voltage in the positive side, which is called as upper threshold voltage. And you can also calculate this reference voltage on the negative side, which is called as lower threshold voltage. Okay. So here, whenever you see the analog wave here, it is less than the upper threshold voltage. It is less than the upper threshold voltage, the output is positive. The output is positive, it is plus Vsat. One value only, it is constant. It is not varying, it is constant at one value. When the output goes above here, above the threshold voltage, the when the input goes above the threshold voltage here you can see the output will change its state from plus Vsat to minus Vsat. So this change, what you see here, from plus Vsat to minus Vsat, this comes when the output goes above the threshold voltage of the upper side. Again, when you see when the input is varying like this, when the input comes to a point where it becomes less than the lower threshold voltage, the output which was at minus Vsat here will change its state to plus Vsat. So it comes to plus Vsat here at this point. Again, when the input varies from the negative and goes to a point where it is going to cross the upper threshold voltage, then this plus Vsat will be changing to minus Vsat. So there is a condition whenever the input goes above upper threshold, the output will be minus Vsat. Whenever the condition goes below upper threshold, it is minus Vsat. And whenever it goes below lower threshold, it goes with plus Vsat. Okay. So it will be minus Vsat whenever the input is upper with the upper value with the threshold of the upper threshold, and whenever it goes below the lower threshold, the output will be plus Vsat. Okay, in this way, the output is going to change from plus Vsat to minus Vsat, and you can see that the input is an analog wave and the output is a square wave. So you can call it as input is a analog wave and the output is a digital wave. So in case of Schmitt trigger, hysteresis means that the circuit triggers at different voltages to switch the output from one state to other. Now this you can see here. Now, if you are seeing this waveform here, this is your input waveform. Okay, this is your input waveform. This is the upper threshold. This is the lower threshold. Okay. Now, if you see between upper threshold and lower threshold, this area, okay, this area from this point to this point, it is not changing. The output is not changing. It is remaining same minus Vsat. Similarly, here you can see from this point to this point, okay, between upper threshold and lower threshold, the output is not changing here. It is same. Only it has changed here and it is changing here, but here it is not changing. It remains same. So this part of the response of the output, that is between VUT and VLT, can be plotted like this as shown here, and that is called as a dead band. That is called as a dead band, and that dead band is indicating your hysteresis loop. So here you can see, if you draw the graph of V out and V in, okay, V out and V in. So here you can see this is V out and this is V in. Okay, so if you take the area of between upper threshold and lower threshold, you can see that there is a dead band. There is a dead band. The output will be between plus Vsat and minus Vsat. Okay, so this is called as a hysteresis loop. So if you want to see the applications of Schmitt trigger, we can say that Schmitt triggers are mainly used for changing a sine wave to square wave. They must be utilized in the switch debouncer circuit for a noisy, otherwise slow input requirements like to be cleaned up or speed up. These are normally utilized in applications like signal conditioning for removing signal noise in digital circuits. These are used to implement relaxation oscillators for closed loop negative response designs. These are used in switching power supplies as well as function generators. Okay, so these are few applications of Schmitt trigger. Thank you, students.